All right, I think we're ready to go. My name's Steve Blackburn, and I'll be chairing this session. I'm at Google and the Australian National University, and our first speaker will be Hongfei Fu, who's at Shanghai Jiao, and he's going to talk to us about static posterior inference of Bayesian probabilistic programming via polynomial solving. So thank you, Hongfei.
The Guanyan and also Professor Lu Kang. Next. Okay. The background of the research is that we try to write Bayesian models as programs, and then we try to perform inference over such programs. So here we aim to solve this Bayesian inference problem over Bayesian probabilistic programs, and actually there are two classes of methods, such as process methods and also static analysis methods. So if we adopt the process methods, then we aim to derive an estimate of this posterior distribution in a lightweight fashion. And if we adopt this static analysis methods, then we aim to derive exact bounds for this posterior distribution. Okay. So here, to solve this posterior inference problem over Bayesian programs, then there are several previous works, such as the first one, which is the most suitable one, which is through process methods. So we have that we can perform this approximate estimate of Markov Chain Monte Carlo, and then we may also solve this problem of variational inference. But here we focus more on this guaranteed bounds, which adopts static analysis method. So there are several previous works, such as for bounded loops. We can unroll the loops to obtain the whole behavior of the loop, which has been implemented in various programming languages, and there are also several works to address this guaranteed bound problem via over unbounded loops, such as one can use this general function method to solve unbounded loops with discrete probability distribution, and we may also use this recursion unrolling and tries to abstract the continuous distribution via intervals, and also use widening to terminate this unterminating cases in unrolling. This is implemented in GBPI. So here we propose a polynomial solving method to handle Bayesian programs with unbounded loops and also continuous distributions. So here is the outline of our approach. So we use fixed point theory and also optional stopping theorem, and we use constraint solving for polynomials, which has been done for a while. Our major novelty lies at the truncation operation, which is crucial to adapt polynomial solving methods to the posterior inference of Bayesian programs. And we evaluate our approach with this GBPI, which is the most rated tool. Yeah. Okay. So we'll first review some mathematics behind. So here, here we use fixed point theory where we can derive a prefix points to serve as an upper bound for the posterior distribution, and a postfix point as a lower bound if we have if we guarantee that the program terminates officially, which ensures that we have a unique fixed point. And we also use optional stopping theorem, where it is one thing that we can use supermatrix to derive upper bounds, and also submatrix to derive lower bounds. Okay, so these things are all done. And here I would also like to remark that so here we have a bit non-classical setting for our posterior inference problem, because here we introduce weights, and we have weights which is multiplicative, which means that if we have a weight statement like score, see here this is a score WT, and then we multiply this WT value to the current cumulative weight to obtain the new weight. So here weights are multiplicative, and also we define the posterior distribution from the weights above. So our contribution is that we first apply polynomial solving, which is none, but we find that simply apply this polynomial solving does no service to solve this Bayesian inference problem. So we propose a novel truncation operation. So the intuition is that we somehow restrict the program behavior onto a bounded range of program values, and then we accompany this truncation with bounds outside of the truncation. So that if the bounds outside the truncation are correct, then we can get the correct bounds for our posterior distribution. So we also in our research we find that for several Bayesian inference problem, we have that somehow we need to deal with ways that gets multiplied again, so that there may be an integrability. So there may be an integrability issue inside the problem. So to handle this issue, we somehow propose a multiplicative variant of this OST, which is optional stopping theorem, and we find that this works to address this issue. So we'll see later. Okay, so we illustrate our approach about this. I think very standard example. So this example is that it models a random walk of the pedestrian. So you can see that from the first line of the code, we have that we assign the variable stat with a value which is uniformly chosen from 0 to 3. So if you are familiar with the Bayesian inference, then you know that this is a prior distribution, which reflects the prior belief of the initial parameters. And then we have working variables, which is post and state, which means that post records the current position of the pedestrian, and this records the current. It records the total distance traveled so far by the pedestrian. Then the behavior of the pedestrian is stochastic. It is specified by the loop below. So we have that until post is until post is smaller than 0, which means that until the pedestrian arrives at the origin, so he repeatedly have a movement where the movement is either forward or backward with probability both 1/2, and along the direction we have that the travel distance is also stochastic, which is uniformly sampled from 0 and 1. So this is a while loop, and we know that this loop will terminate with further 1 because it is a symmetric random walk, and at the end of the program, we have this score statement, which is the score of this normal 1.1, 0.1, which is the density function of the normal distribution with mean value 1.1 and variance 0.1. Yeah. So this score statement says that the pedestrian finds that the total distance traveled so far measured by odometer, it is 1.1, but with normal error. Yeah, yeah. So we return this start variable to so the start variable is the initial parameter, which means that we wish to perform the posterior inference for this initial parameter. Yeah. Okay. So here some remarks on how to define this posterior distribution. So here we have the so here we first define this expected weight. So given a subset U of real numbers, so we simply define this expected weight restricted to this U as the expected weight when the return value is falls within U, and then we define this normalised constant, which is the unrestricted weight over the whole real line, and then we define this posterior distribution as the ratio against this normalised constant. Okay. Okay. So the problem now arises on how we analyze this posterior distribution. So we could apply polynomial solving, such as we can sketch the main steps here. That we have a polynomial template at the entry point of this while loop, which is here. It is h in blue, and then we can apply prefix point conditions to this h, whose details I do not wish to go into. It is sort of calculating the expected value of h after one loop iteration of h, and then we have that this expected value is smaller than or equal to h, and then we apply polynomial solving to this inequality. So these things are all known approaches, but we find that simply by applying this, we only get the constant bounds. So it seems that there is some problem inside, and we find that the problem is that for this working variable post and dist, we have that their values in this program they can be unbounded. So they can take any value, any non-negative real value. So somehow polynomials are not so effective on this unbounded region, as someone may recall that we have Weierstrass process theorem, which states that any continuous function can be approximated up to any error by a polynomial, but only over a bounded region. Yeah. So here, to make this problem solving effective, we need to have a truncation operation that first truncates the value of post and dist onto a truncated range. A bounded range, and then we have that, and then we try to solve, try to apply the polynomial solving over this bounded range. So So here we see that we first apply this truncation where we specify it to 0.5. I mean the square between 0 and 5. So that is the value of both post and dist. It is within 0 and 5, and then we somehow derive an upper bound outside the truncated range. So here you see that it is very small, which is 2.1 times 10 to minus 330. So this bound can be derived by examining by looking at the monotonicity of this program. So it can be easily derived, and then with this truncation range and also this upper bound, we then solve this problem solving over only over this truncated range. So here we see that this truncated prefix point condition. Here see that the expected value of so here it is a summation which is b prime times h prime plus b prime times m, which so here this m it is it should be the second one should be the negation of b prime. Which means that it is outside the truncated range. So here the prime means that we have performed one loop iteration, and if it is outside the truncated range, then we simply have this upper bound m here, and if it is inside still inside the truncated range, then we'll have this have this h prime here, which is still the one-step expected value from h after one loop iteration. Yeah. So after this we have so this is the key step of truncation. So after this truncation, we can solve this Bayesian inference problem over this example. So okay. So yeah. So there are some assumptions for problem solving. For example, we need to have a polynomial approximation for the score function, because here you see that the score function is not polynomial. So we need to have certain polynomial approximation to this, and so because in the whole process we only allow polynomials. So here we need to have polynomial approximations whenever possible. Yeah. Okay. So so here in our research we find that there are some Bayesian inference problems which has a score of weight greater than 1 inside the nobody. So if we have unbounded loops here, then it may be the case that the score value may incur an integrability issue. So here we derive a new OST variant to handle this case. Yeah. Okay. So so this is our overview of our algorithm, and you can see our experimental results. So these are for the posterior inference. So you can see that. Since I do not have enough time, so I just quickly go through these results. You can see that the bounds of our approach are quite close, and we also have evaluation on a certain probability, and you can see that our bounds are also quite precise. Yeah. So thank you for your attention.
Thank you very much. If someone's got a quick question, I'm sure we can do one quick question. I think we've only got time for one, though. So please state your name and affiliation before you question.
So I'm Peter from University, Czechia. Thanks for the talk. I have a question about this new variant of the OST. So this condition that the change is kind of multiplicatively bounded, that's a absolute one-step change or expected in expectation?
It's still absolute, yeah.
And there are, like for these additional extensions by Wang et al. From the previous literature, they typically impose some additional conditions like exponentially decreasing tail bounds.
Yes,
Do you
yes.
also have something like this here?
Yes. We use this to cancel out this multiplicative scaling of score values. Yeah.
Okay, thanks.
Right, thank you very much.